Thanks for having me. Thanks for being here. And well, because as Angela's pointed out, I'm involved in both maths and music. Something that often happens is when people who know me from one of those disciplines find out about the other, they say, "Oh, maths and music, they go together, don't they?" It's a very common remark. But most people don't really know much more beyond that. They just know that they go together. And I always have to stress when people point this out that yes, they do, but they do and they don't. It's a limited sort of compatibility. There are many aspects of music. Some of them can be understood and analysed in terms of mathematics and number, and others can't. So, because I was asked to talk about the connections between mathematics and music, I'm going to be dwelling on those aspects of music which can be quantified and reduced to number. This doesn't mean that that's how I see music or how I think music should be seen. I want to stress before I start that really the aspects of music that we like, the important ones to me, are the ones you can't reduce to a mathematical analysis. The beauty of music, the way that certain passages of music can stir particular emotions, the mysterious, intuitive dimension of group improvisation, and just the fact that humans make music, that all over the world people make music. This is a huge part of human culture and it has no obvious biological survival value. So there are many mysterious and unquantifiable aspects of music which are important to me as someone who makes music and which can't be reduced to mathematics, but I'm going to talk about the ones which can, so that's my disclaimer. But I have a more astute friend, he's a musician but not a mathematician, who said something a little bit more detailed, or observed something about maths and music, or about number and music. And he said he'd come to the realisation that music is all about the subdivision of time into equal amounts, so chopping time up into equal time intervals. And we talked about that for a while, and I saw where he was coming from. So we're going to look at that idea to start with. So music, the three main elements of music as it's generally understood, melody, harmony and rhythm. Different musics from different cultures, different parts of the world stress some more than others, but these are the three basic components. Now melody is that's the mysterious one. That's the one that seems to just be, it's just the gift that descends upon people, which you can't really reduce to a formula or an algorithm or a mathematical analysis. People will try, of course, to try and work out why some melodies appeal, but that's the thing we can say the least about. So I'm not going to say much about melody at all. Harmony is all about subdividing time up into equal amounts, and that's going to be the main chunk of what I'm talking about tonight. And rhythm, I think everyone gets that. Rhythm is about cutting time up into equal amounts. I think you can all understand what I mean by that. And as a way of illustrating that fact, so I'll just say a little bit about rhythm before we get into the main chunk of the presentation. Engineers for years have been using the abbreviation RPM because revolutions per minute, the number of times something spins around. It's such a basic thing in engineering that we have an abbreviation for it. And in the last 20 years, with the rise of electronic music, DJs and producers have got their own abbreviation now, BPM, beats per minute. So it's the same thing. You're basically taking a minute, you're chopping it up into a certain number of time intervals, and you've got a marker at each interval, which is a beat. And so rhythm is the subdivision of time into equal amounts. But it's not just that. Because if there's someone next door hammering, and they're hammering very rhythmically, but that's all they're doing, it's just bang, bang, bang. That's rhythmical, it's got a beats per minute you could work out, but it's not musical. It's just annoying. Although perhaps some avant-garde minimalist composer might make a piece of music out of somebody hammering, but a washing machine has a steady rhythm, but it's not musical. To make rhythm musical, you need some sort of cycle. You need every number of beats, something to sort of happen again or come back to where it was. You need some basic motif to repeat or at least transform itself. And anyone involved in music knows about something called time signatures. So you have a piece of music would be in 4/4 or 6/8 or 11/8. And what these pairs of numbers refer to are the size of the bits of time you're cutting up, whether you're cutting time up into eighth notes or quarter notes, or this all depends on how fast you're playing, but there are basic subdivisions which are agreed upon. So you're chopping time up into intervals of a certain size, and then every 3 of them, or 7 of them, or 4 of them, something's repeating. So in, say, 7/8 time, you're counting out eighth notes, which are of a particular length according to the tempo you're playing, and every 7 of those, there's some feeling of you've come back to where you started. So there has to be this cycle. Now, in not so much in Western music, but in Indian classical music and in a lot of African music, you have polyrhythms, and you get them also in modern classical music and in some experimental rock music and in techno, all sorts of places. They're very basic. But the idea of a polyrhythm is not just a cycle of beats that repeats, but 2 cycles going on, or 2 or more, but usually 2 cycles going on at the same time, which are different cycles. So they sort of go in and out of phase with each other and then loop back together again. And if you've not come across polyrhythms, it's worth experiencing this directly. So we're going to have just a little moment of audience participation. So this is the bit, rather like certain concerts where they get the people on that side of the mixing desk to do something, the people over here. So the people on the left, you lot over there, I'm going to count to 12 over and over and over in a loop. So I'm going to cut time up into equal amounts. And you're going to clap on the multiples of 3, so the parenthesized numbers, 3, 6, 9 and 12. When you hit your numbers, you clap. People on the right, you're going to be clapping every multiple of 4, so 4, 8 and 12. So both groups of you are clapping on the 12. So one of you is doing a 3 cycle and one's doing a 4 cycle, and the 2 lock together. So I'm just going to count and you're going to clap. Is everyone ready? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. That wasn't the best demonstration of polyrhythm ever, but that's what you've got. You've got 2 interlocking cycles, and we'll come back to that because I've discovered something about polyrhythms in the process of putting this talk together, which I was very surprised by. It's not an original discovery, but it's an interesting one. So that's rhythm understood in terms of number, obviously. Now we're going to go on to harmony, but before we get on to harmony, we have to understand the basic element of what we're dealing with, which are tones. Tones, notes, whatever you want to call them, pitches. If you play a C or an F sharp or something on a piano, what is that? What's going on? Okay, well if I play a violin or blow a trumpet or sing, something is vibrating. Something is whether it's my larynx or it's a piece of metal or it's a piece of catgut, it's flapping back and forth on some very small scale, and it's creating waves in the air. It's creating pressure waves that emanate out from that point. So it's like throwing a pebble in a pond. You see the ripples move out. How heavy the pebble is and how hard you throw it is going to affect the nature of the waves which emanate. Similarly, if I'm singing, which is just as well, I'm not going to sing. I'll spare you that. But if I were to sing a note, my larynx is vibrating a certain number of times per second. Now, these various notes that could be sung or played on an instrument can be represented mathematically as these things, sine waves. Basic element of engineering, but any kind of acoustic theory, you'd be dealing with these. And the horizontal axis represents time. The vertical axis represents how loud the note is. In this case, we've got 3 examples. They're all the same volume. The amplitude is the height of how high and low the wave goes. But what's important is how often it crosses the horizontal axis. So the wave at the bottom crosses the horizontal axis a lot more than the one at the top. It crosses it more frequently. It has a higher frequency. This is what frequency refers to, is how often something happens. So it's something spinning around or cycling or vibrating. There's a number of times per second that's happening. So the thing at the bottom would represent a higher pitch than the thing at the top. You have low bass notes with long wavelengths and low frequencies, and you have high notes, treble notes with short wavelengths and high frequencies. And these are the basic elements we're going to be dealing with. Now, if you take your frequency below about 50, the human ear can hear frequencies between about 50 cycles per second and 20,000. Everyone's ears are different, but the highest notes you can hear are about 20,000 and the lowest are about 50. Once you get below about 50, something interesting happens, because if you are clapping a certain number of times a minute, or you're playing a drum beat, it's the same basic idea. Something is repeating, but it feels like a very different kind of thing to hit something rhythmically and to play a violin note or sing. But in fact, if you imagine, if you speed it up, if you had a clicking sound or a beat, and you speed it up, it becomes a buzz. And if you speed it up even more, the buzz becomes a kind of whir, and then a whine, and then it starts singing. You can imagine this, it's sort of, and then it comes, and then, and it gets higher. And then eventually it's like rubbing your finger around a wine glass, it becomes a note. So basically, rhythm and not melody, but pitch or sound, musical sound, are the same thing, just at different speeds. They're not qualitatively different, they're just quantitatively different. So anything below 50 cycles per second, you don't hear as a bass note, like the really deep bass that you hear is maybe, I don't know, 80 to 100, I'm guessing, cycles per second. But anything below 50, you just hear a click, you hear a da-da-da-da-da-da, you hear a sort of buzz. And rhythm is below that. So below 50 is rhythm, above 50 is a sort of musical sound. And this is again important because what we were doing with polyrhythms there, I'll show you how that relates to the notion of harmony shortly. But the numerical basis of musical harmony, as I've said, this is the main thing I'm going to talk about. And this takes us right back to the very beginnings of Western mathematics. This character, Pythagoras, I don't know how they knew what he looked like, but he was around 500 BC. And he was sort of the first mathematician. He's often credited, he proved, or no, he didn't. He's credited with having discovered the Pythagorean theorem, this a squared plus b squared. Well, I won't go into that, but triangles with right angles, they conform to this theorem that Pythagoras supposedly discovered, or is attributed to him. But more interestingly than his geometry was this assertion that he supposedly made. Again, we don't know much about him, we don't know much about his followers. We know there was a sort of cult around him, men and women were both welcome. They had quite strict rules of diet and hygiene. They're vegetarians. Apparently the word vegetarian is 19th century. Before that, if you didn't eat meat, you were called a Pythagorean, which is interesting to me. But people know a lot about, or think they know a lot about the Pythagoreans and their way of being, but reading up on them, I discovered actually we don't know much at all. There's very little original, there are very few original texts. There's just various people's commentaries that came later. They were a persecuted group, so they survived for a couple of hundred years after Pythagoras. No one really knows quite what was going on. It was kind of like a mystery initiation cult or something like this. But there was a fixation on number. As I said, Pythagoras is attributed with this all is number. And what meaning, as I understand it, numbers constitute the true natures, the true natures of things. And Aristotle, I found this, I thought this was interesting because I've not come across it before. This is Aristotle describing, so he came a couple of centuries later, I suppose, and describing what the Pythagoreans were about. He said the Pythagoreans too held that void exists and that it enters the heaven from the unlimited breath. It, so to speak, breathes in void. And this is the interesting bit. The void distinguishes the natures of things, since it is the thing that separates and distinguishes the successive terms in a series. This happens in the first case of numbers, for the void distinguishes their nature. So what he seems to be saying is, anything that repeats, whether it's drum beats or a row of trees that you've planted, the thing that makes them separate from each other is the space between them. If there's no time in between the beats, it's just one noise. If the trees are all planted in the same place, it's not a row of trees anymore. Similarly, numbers, if you write them out on a line or if you count them out in time, if there's no gap between them, they're not really there. So the numbers are somehow distinguished by the emptiness around them. And Aristotle's suggesting that this is what the Pythagoreans, this is why they were interested in number, because number is the sort of archetypal instance of when the void starts to distinguish separate things. And what grabbed me about that particular phrase was how close it is to there are certain passages in the Tao Te Ching, the ancient Chinese Taoist text, which talk about the usefulness of a bowl being the empty space inside it, or the hub of a wheel or a window frame. It's the emptiness which is the essence of the thing. So anyway, that's the sort of, we'll get back to music quite soon, but what we need to know about the Pythagoreans is they're interested in number, but it wasn't so much individual numbers, it was the relationships between them. And so we need to know about whole number ratios. And a ratio, there are various ways, I've given 3 examples here, and there are 3 ways you can you can represent them. They're all equivalent. The one in the centre is the most familiar, or the most common, I mean, using a colon. So 2 to 3, 5 to 8, 117 to 3,882. You can also write them as fractions, as on the left, 2 over 3, 5 over 8, or you can write them with the word 2, as on the right-hand column. The fraction's a bit confusing because that suggests you can actually do the dividing. You can divide 5 by 8. And that's not what it is. It's not the result of dividing one number by the other. It's the relationship between the two. And that might, if that sounds a bit abstract, let's make it visual. So here we've visually represented ratios. I've put times in between the numbers for some reason, but you could equally put the colon or anything else. So the ratio of 7 to 5 can be represented by this rectangle. So we've got 7 squares and 5 squares. Now the thing about that rectangle, it doesn't matter how big or small it is. I mean, how far away you're sitting from the screen, or if I were to zoom in on the screen, it's the same shape. The shape doesn't change. It's the ratio 7 to 5 encodes the shape of the rectangle. 1 by 1 is a square, however big or small that square is. And any two numbers you like, any two positive counting numbers, you can make one of these rectangles, and it represents a ratio. But the thing is, so it's a proportion, it's representing a proportion. But what about these? These are proportions as well. These are rectangles that haven't got grids on them. Now, is it possible to make these conform to a grid? This is a question. Is it possible? Now, with these sorts of things, there's a trick you can do. If you can't be bothered to count, if you had a huge one that was thousands of squares each side, there's a trick where you can find out what the dimensions of it are by chopping squares off. This one here, if you were to chop off a square, you're left with a long thin thing on the edge. You tip that over and then you chop squares off until you're left with something, and you tip it over and you chop off squares. Eventually that's got to stop. I think everyone can agree, if we chop squares off the sides of these rectangles and then chop squares off the sides of at some point we're going to be left either with a single square or a square of a larger size. But eventually you can dismantle these things. The question is, if you're given these rectangles without squares on them, if you start cutting squares off the sides of them and following the same procedure, does it always stop? Do you always end up with a square? Now you might think, well, it's going to get so small in the end that it might as well be. You know, you're going to end up with some tiny little piece of paper. And also these things have got thick black edges. They're not particularly well defined. But we're talking in pure mathematical terms. We're talking about a ratio of two numbers or a proportion of two quantities. And the question is, it's an equivalent question. Can you eventually dismantle that into squares? Or can you find a size of square where you can superimpose a grid over those perfectly? So they're not like 37 by 51 and a bit. They're like exactly a grid of squares. Is that always possible? And this was something that the Pythagoreans were concerned about. Can every quantity be represented as a ratio? And it turns out no. There's this thing that they got very interested in, which a lot is being written about and said about, and it's generally, a lot of it is misguided, I'm afraid. So beware if you're reading about the golden rectangle. There are all sorts of mistaken claims about its role in architecture, art, biology and all sorts of things. But it is very important, and it's a remarkable form, being, for the reason that if you cut a square off the side, what happens is you're left with this, yeah? And if you turn that, if you cut that off and turned it on its side, it's the same rectangle you started with. This is the only rectangle that does that, where if you cut a square off the side, you end up with the same thing. So that means if you then cut a square off that, you end up with the same thing again. This is exactly the same proportion as the one you started with. And you cut a square off that, you end up with another one but just turned on its side, and it goes on forever. And you can draw a beautiful spiral. If you take sort of quarter circles in these squares, it spirals down. But the point is it goes down forever. You can keep cutting squares off, it never ends. And because of that, it's impossible. However small your squares are, there is no size square where you can fit a piece of graph paper over that and it's a nice, neat fit of whole numbers. It's never going to be whole numbers. It's an irrational number. And this is what the Pythagoreans were shocked to discover, because they believed that everything could be understood in terms of ratios of whole numbers. And this brings us back to music in a second. This is the irrational number that they're generally thought to have been shocked to discover. If I have a square, it's the one that you come across most often in a sense, the golden rectangle you might have heard of. But anywhere you see a square, anything square, you can draw a diagonal, can't you, from one corner to the other. And if one side of the square is 1 metre or 1 inch or 1 anything, what's the diagonal? Anyone know? Yeah, according to Pythagoras and his theorem, it's the square root of 2, because this times itself is 1, and this times itself is 1, and 1 plus 1 is 2, so this is going to be the thing that times itself is 2. What times itself is 2? Some people guess 1.5, but no, 1.5 times itself is 2.25, so that's too big. 1.4 times itself is a bit less than 2, so it's got to be bigger. And that number down there, this is the number at the bottom here, that if you multiply it by itself, you get 2. And as you can see, it doesn't seem to follow any obvious pattern. If you keep calculating it, it just goes on forever and it doesn't repeat. And because of that, if you were to take this and use them as the sides of a rectangle, you get the same thing. You get a rectangle. It cannot be reduced to squares. It can't be broken down into a whole number ratio. And this was shocking to the Pythagoreans because they thought the whole universe was based on this harmony of ratios. And this is the bloke who got the blame for it, Hippasus of Metapontum. There's almost nothing is known about this, and it's all completely apocryphal, but there's some quite interesting stories that have come down to us. And there are variations on the story, but basically it seems Hippasus of Metapontum either discovered the existence of irrational numbers, or he leaked that discovery out into the public, and as a result, according to the stories, got drowned at sea by his followers. By Pythagoras' followers. There's even a sort of Hollywood-style version of the story where Pythagoras himself condemns him to death while they're all out at sea and they chuck him overboard. But it doesn't really matter what happened or if it was him. The point is the story indicates how shocking to their worldview it was that there could be numbers that were not ratios. And it's not clear. Usually when you read about him, they say he proved the square root of 2 was not rational. But that was Euclid. Euclid definitely knew that in 300 BC. About 200 years later, Euclid had made that clear. But it's been argued that he didn't have the logical mathematical tools to have proved that, so it's unlikely that he did. And it's another irrational number, in fact, that he discovered. And this is interesting. If you start with, this is the golden rectangle we were looking at a moment ago, and you take one side off it, so you've just got the 3 sides. Imagine that's made of some sort of rigid wire, and then you bend the 2 sides together, you get this triangle, yeah? Now that triangle might look familiar, because it's this triangle. It's the spike on a pentagram, and this was the symbol that the Pythagoreans used as their sort of ID symbol, like the Christians a few centuries later had the fish. I think they might have had it tattooed on their hands or something like that, but that was a sign that you were part of the group. And it's been adopted by Wiccans and Satanists and all sorts of people, the European Union. But it's full of the golden ratio. That rectangle, I didn't actually tell you what it was. Or did I tell you what it was? It's 1.618. There we are. The ratio of this side here, the short side to the long side, is about 1.618. And that ratio is all over this thing. If you start measuring the relationship between a short bit and a long bit, it's always in that ratio. And what has a more convincing argument, rather than the square root of 2, was that he realised that you could start with the pentagram and you could make an upside-down pentagram inside it, in this pentagon here. You've got an upside-down version of the star you started with, and inside that is a pentagon, which you can then make a right-way-up pentagram inside, which has got an upside-down pentagon in it, and you could make a pentagram inside that, and it goes on forever. And I won't bother you with the argument, but Hippasus, with the mathematical and logical concepts available at the time, could have argued, we don't know, that because of that infinite descent, the ratio of the short side to the long side, the short side to the long side, the short side to the long side, all of these ratios can't be a rational number. If it was rational, if you could make it into a ratio, that process would have to end. And we can all see there's nothing to stop it. It just infinitely descends into that centre point. So, on to the musical aspect of Pythagoras. So another apocryphal story is that Pythagoras was walking past a blacksmith's workshop, and he heard the hammers hitting the anvils, and he heard musical harmony. And he went in and asked if he could weigh their hammers, and weighed them and found they were in whole number ratios, the weights of the hammers. in ratios of 2 to 3 or 1 to 2 or something, 3 to 4. Hence, you see here, this I don't know who did this woodcut, but there's numbers on the hammers that are in these ratios. And so he supposedly was intrigued by this and went away and started experimenting with bells and cups and strings that are at different tensions and flutes of different lengths, and found that basically musical harmony can be understood in terms of whole number ratios. And this is what we can thank if not Pythagoras himself, the people around him at that time started to understand musical harmony in terms of whole number ratios. What was going on before that musically, I suppose very little is known about. I certainly couldn't say anything about it. But this is a tool that the Pythagoreans would have been using, and various people since. It's not so much a musical instrument as a sort of experimental tool or a tool for educational purposes. It's just a one-stringed instrument, and the idea is that you tune it to just a whatever note. It doesn't matter what note it is, to be honest. And then you stop it with your finger at some point along the string, and you twang it and you get a note, and then you release it and you twang it, you get another note, and you've got these two notes are in a sort of proportion. And it turns out that if you put your finger halfway along and you twang it, you get a note which is related to the note you get if you twang it unstopped. And in the relationship's called an octave. If you stop it 2/3 of the way along and you twang it, then you're twanging two strings in a ratio of 2 to 3. And you get another musical harmony. And we'll talk about that in a second. But something else that happens when you, this is quite important, when you pluck a string on a monochord or a guitar or anything, any stringed instrument. So this represents the two ends of the string here, and we see, you can imagine the string sort of vibrating up and down a certain number of times per second, and that will be related not to how hard you pull it or hit it or bow it, but to the length of the string, the weight of the string, and the tension. Those are the three factors that determine the note. How hard you play it determines the amplitude of the wave, but the wavelength is fixed by the length of the string. So this is the note itself. It's the wavelength of the note is determined by the length of the string. But if you do that, you get these other, what are called standing waves. These are called overtones. And you can fit 2 of these arcs onto the length of the string. You can fit 3 arcs of this length onto the length of that string, and you can fit 4 of this length. So when you play a note on a guitar or any stringed instrument, you don't just get the note, you get these other higher notes. Each one is higher than the others. You get this infinite sequence of higher and higher overtones. Now, most of them you never hear. Most of them are ultrasonic. They're beyond what the ear can hear. And also, because of the physical limitations of the instrument, a lot of them aren't very audible. But good instrument makers exploit this. The reason certain guitars sound a certain way, and the reason some instruments sound different from other instruments, is because the architecture of the instrument, whether it's made of wood or metal or whatever, is such that certain overtones are more prominent than others. And a really striking example of this is a clarinet or a single reed instrument. A clarinet's a very good example of it, though. I think it's only the odd, it's either odd or even, but I'm pretty certain it's the odd. You only get the odd numbered overtones. The even ones you just don't hear. And because of that, you hear that sound and think, oh, that's a clarinet, rather than, oh, that's a trumpet. So what our ear is picking up on allows us to distinguish one instrument from the other. Isn't the note it's playing, because of course, the note's just the note. It's this blend of different overtones. Now, it's possible, the best way to hear the harmonic series is with a thing called an aeolian harp. Now, these go back to ancient Greece, Aeolus being the god of the wind, and the Victorians were fascinated by these as well. You can make, these are 2 sort of quite big ones, 2 different designs, a sort of slightly more traditional harp-shaped one and a modern one. You can make quite simple, small wooden boxes. And the idea is basically, or you can just take a harp, just an ordinary harp held into the wind. We'll do this if you press your ear against it. And I shall play you, just it's worth hearing if you've never heard one before. So this is what an aeolian harp sounds like. So you're listening to the harmonic series, you're hearing, it doesn't really matter how you tune it, you get the same sound. And it's changing, these sort of waves are coming in and out, and it's to do with the wind changing. If the wind's steady, it will just ring in one way. what I think happens with the wind changing, you're getting certain overtones in the harmonic series coming more to the fore. So it's like a big group of people standing in line, and occasionally the line sort of is wavering. But this is what the harmonic series sounds like, and it's. I was going to say something about that. Anyway, oh yeah, the physics of it's quite interesting. No one really knows how they work, but the best theory going is that the wind breaks up behind the string, and it creates little tiny whirlpools. You know, when you see the wind, you know, it's sort of in the cities often where there's sort of corners and things, it's a windy day, you see leaves spinning around in a little whirlpool. Well, you get the same thing, but just microscopic. So these tiny little microscopic air vortices forming behind the strings set the strings ringing, rather like when you rub your finger around the top of a wine glass, or if you've ever seen a hurdy-gurdy, the idea of a wheel resonating a string. So there's just this continual ringing sound. The string isn't being plucked by the wind, it's being sort of rung. Anyway, that's the Aeolian harp, that's the harmonic series. But musical intervals, this brings us back to Pythagoras. As I said, with the monochord, you can stop the monochord 2/3 of the way along, and then you've got a ratio of 2 to 3 if you play it stopped and unstopped. If you stop it 8/15 of the way along, which is just over halfway, then the ratio of the two tones you played, the stopped one to the unstopped, is 8 to 15. And we're talking about the ratio of the wavelengths, because where you stop the string is how long the wave can be. So the basic elements of musical harmony are these intervals. Now these aren't notes, these are gaps between notes. So it doesn't matter what the first note is, the interval determines what the second one's going to be. And it's to do with ratios of frequencies. And I'll have to play you some of these so you can hear what they sound like. So octaves are the most familiar, the most basic of these. So an octave, 2 notes. Now we've all heard that, and they're kind of like the same note. They're the same note but on a different level, and they go together, because if you play them together, it's almost like it's just one thing, isn't it? But that's 2 notes at the same time, but it's the same. What's going on is you've got 2 wavelengths in a ratio of 1 to 2. So you've got a wavelength and a wavelength half as long. So two of the short ones fit exactly onto one of the long one, and you get this kind of consonance, this musical consonance. Don't know what's happened here. Just try again. Okay. Now the next interval that's most common in Western music, all over the world in fact, is the fifth. And the fifth is the ratio of 2 to 3. I did it again. So that's if I pluck the string 2/3 of the way along, and then I pluck it unstopped. The ratio of the 2 wavelengths is 2 to 3, and the 2 notes will sound like this. And I'll stress, it doesn't matter what the first note is, it's that relationship that's important. And if you play them together, now you can hear there's 2 notes, but they sound really nice together. Everyone agrees there's a nice consonance in those 2 sounds. And you find that all over the world. And the ratio is 2 to 3. So what that means is you've got a shorter wavelength and a longer wavelength. And that 3 of the short ones are the same as 2 of the long ones. So you play those together and something meshes together. Now the next simplest one is a ratio of 3 to 4. So that's if I pluck the string 3/4 of the way along. So the short one is 3, the long one is 4. The 2 notes sound like this. And you play them together. Also quite a pleasant sounding consonance. And it turns out the fifth and the fourth, and these names by the way are confusing, 5th, 4th, 5th, 7th, 2nd, they don't matter. They're the result of Western music theory and certain scales which have come into favour. They refer to different notes of scale. They don't come into what I'm talking about. It's the ratios that matter. And a fourth, what we just heard there, is a 3 to 4 ratio. A 3 to 4 ratio, so that's a short wave and a slightly longer wave, and 4 of the short ones lock perfectly into 3 of the longer ones. And if you think about that, hang on a minute, we were clapping earlier, and you lot were clapping 3 times a cycle, and you lot were clapping 4 times a cycle, and they were locking together. And then I said something about how rhythm and pitch are the same thing. It's just rhythm is slow and pitch is faster. Anything below 50 cycles per second you hear as a beat, and anything above it you hear as a note. What that means is if I recorded you clapping your 3/4 polyrhythm and you got it right, and I'd sped it up hundreds of times, I would hear this. It would sound like that. it was only in putting this talk together I realised that. I thought, hang on a minute, you speed up a polyrhythm, you get some African drummers to do a really sort of tight 7/8 polyrhythm or something, and then you speed it up. You make a recording, you speed up, you'll hear a musical harmony. Wow! Nobody told me that. So I thought, well, I'll Google to see if anyone else, surely someone's noticed this. I Googled it, and Stockhausen discovered that. But no one else, me and Stockhausen. Stockhausen, I think, did some experimental composition based on speeding up polyrhythms, and no one else seemed to care. It's just like, oh yeah, that's kind of interesting. But no, what this means is that polyrhythm is the rhythmic version of harmony. That if you slow harmony down enough, it becomes polyrhythm. So it's the part of us that responds to it, arguably, is the same part. Anyway, now we're going to get onto some sort of Western corruption in music, effectively. These are the Pythagorean ratios, these fractions, these ratios, whole number ratios that make these beautiful intervals. Oh, there are a few more actually, just quickly run through them. So we have the second, now this is where they start to get a bit more dissonant. This is the second, together. That's not so pleasant, but it would be used in jazz. Thelonious Monk or someone like that would use that. Minor second. That's really dissonant. But look at that, minor second. What's a minor second? It's 16 to 15. So that means you need 16 of the shorter waves to lock onto 15 of the others. It means you have to wait ages for the thing to come round and give you that feeling of completion, which is why it sort of makes you feel a bit tense. So that's a minor second. Minor seventh. That's quite nice. Minor seventh. And that's 7 to 4, you see. That's a 4, so that's 4 waves and 7 waves locking together. So it turns out ancient Greek music, Renaissance music, only used octaves and fifths. And fifths and fourths are kind of the same thing. If you go up a fifth, it's the same as going up an octave and down a fourth. So fifths, fourths and octaves are all linked together. That was the basis of all music up to the 15th century, and then you started to get more complex ratios coming in. You started to get the diminished fifths and sevenths and things like this, and then as jazz and more avant-garde music came along, more and more dissonant intervals were used. Anyway, this is the Western corruption. If you studied music theory, if you play the piano, play jazz, you probably come across the circle of fifths. And this is the idea that if you start with any note, and then you go up a fifth, so remember that's a 2 to 3 ratio. So you've got a note, it's got a number, you're playing a note, so air is vibrating a certain number of times per second. So we multiply that by 1.5. 3 over 2 is 1.5. So we go 1.5 times that, we get another note, and that's called a fifth, that interval. We heard one earlier, and it turns out if you play a C on any instrument, and if you know anything about music, and I say to you, I'll go up a fifth from that, you know that that goes to G. And if you go up a fifth from G, you get to a D. And this idea, I'll play it to you. The idea is that if you go round, if you play 12 fifths in succession, you go up a fifth, up another fifth, up another fifth, up another fifth, you eventually come back to where you started. So here's a cycle of fifths. Okay. So, I said come back to where you started. Obviously you started with and you ended up with, and so the last note was anyway, the idea if you go if you play 12 fifths in succession, as that thing was doing, supposedly you go from a C back to a C, but it's many octaves higher. So on a piano keyboard, you'd start with a C, say with a C, and then you go up to a G, and then up to a D, and you go up and up and up and up, so you end up back at a C. That's the idea. You go around the cycle of fifths, but hang on a minute, going up a fifth is a ratio of 3 to 2, and going up octaves is a ratio of 2 to 1. And if you know anything about numbers, you think, hang on, there's something dodgy here. Because this is telling you, if 12 fifths is 7 octaves, which is what we supposedly just heard there, that means that 3 over 2, which is 1.5, times itself 12 times, say we're scaling up the frequency by 1.5, by 1.5, by 1.5, 12 times, that should be the same as multiplying 2 by itself 7 times. Okay? It's like, is it really? No, check it out on your calculator. It's not. If you multiply 1.5 times itself that many times, 12 times, you get 129 point something. Whereas going up 7 octaves, doubling 7 times, 2, 4, 8, 16, 32, 64, 128. Now 129 is not 128. In fact, it's almost 130. So it's out. So if you go up a cycle of true fifths, 12 fifths, you end up above the 7th octave. It's sharp. It's not what they're telling you. But people started to think, oh, wouldn't it be great if it was? Because then we could change key and we could do all this clever modulation, and then we'd have sophisticated Baroque music. And so they did. They basically cheated, and well, it's often referred back to Bach and the well-tempered clavier. I'll come to that. This is when it happened. It didn't happen quite the way that people often are told. But the idea is, instead of multiplying by 1.5 to get fifth, which is a pure harmonic ratio of 3 to 2, so we're talking about pure Pythagorean ratio, we don't. We multiply by this, 1.498307 something. And if we do that, and then we go up 12 of these fifths, which aren't really fifths, then we do come back to the octave, and that sort of works. And the idea is, well, no one's going to notice the difference. You know, the ear can't really hear it. And it's true. Unless you're a piano tuner or some sort of prodigy, you can't really hear the difference. So there's been this bodge, this fudge, this sort of deceit going on for hundreds of years in music. And it's bad. Well, I don't be judgmental, but I mean, it affects everything. It's not just fifths. The idea is basically, on a piano keyboard, to get from one note to the next, whether it's white or black. Forget the black and white thing, is confusing. You just go from one note to the next note. And that's called a semitone. And the idea is, every time you want to go up a semitone, you multiply by this. This is the equal temperament idea that came along in the late 16th century. No, it's actually 20th century. There's a confusion about this I shall clear up. But anyway, the idea is you scale up your frequency by 1.059, and you've gone up a semitone. Now, if you've got 2 semitones, that's a tone. That's like going from C to D or D to E on a keyboard. Between most pairs of white notes, it's a whole tone. And a whole tone ratio, according to Pythagoras and everyone else before the 16th century, was a 9 to 8 ratio. So it's 9 waves locking onto 8 waves. 9 to 8 is 1.125. That's the pure tone ratio. If you multiply by this slightly dodgy out semitone thing that someone came up with, multiply 2 of those together, you get 1.12, so you're flat. So every single tone you hear in Western music is out. Basically nothing is truly what it should be. And the reason for this was because you could just suddenly do all this amazing stuff. If someone hadn't done that, we wouldn't have Bach, we wouldn't have the Beatles, we wouldn't have anything with key changes in it. It used to be really tricky. You had to change instruments, to have special notes introduced into your instrument, or retune things if you wanted to change key. But just to clear things up, I thought this equal temperament thing went back to Bach, and a lot of people do. But then I found an article online by a mathematician called Michael Rubinstein, who I know is a mathematician, and he's also a pianist, and he wrote a piece called The Conspiracy of Equal Temperament. And he explained that actually that was a 20th century creation. What Bach was using was well temperament. And incidentally, I think the word tempered is from the same, I didn't know this, but I'm guessing it's from the same root as tampered. So if you tamper with something, it's been messed with, the scale has been messed with. But it's been messed with well, it's the well temperament. And every semitone is not the same proportion to the previous one. They're all slightly different. So what they're doing is playing with the ratios of the different intervals so that the cycle of fifths works. If you can get the cycle of fifths to work, you can do all kinds of amazing modulation, and that's what Bach specialised in. But the thing with the well temperament is that different keys sound different, because everything's slightly out in a different way. In equal temperament, if you go up different keys, it's all out, but it's all out in the same way. And it's like on a guitar, if you play a bar chord, you put your finger across all the strings and then you play a shape, you can go up a fret, and it's the same chord all the way up. It sounds the same, but just higher. That in well temperament, it wouldn't be like that. Different keys have different colours. And Michael Rubinstein said he called 20 piano tuners in Austin, Texas, before he found one that could actually tune his piano in well temperament. Everything is equal temperament now. And he was amazed, apparently, playing on it. It's got a completely different feeling. But anyway, this is the standard fretboard on a guitar or any instrument. The only reason it works, this nice, neat thing we call a fretboard, is because of this deceit, this corruption in the harmonic ratios. If you stop the strings where those frets are, loads of them aren't where they're supposed to be. If you want them to be where they're supposed to be, your fretboard looks like that. And this is a guitar designed by Harry Partch, who's a sort of eccentric American musician, theorist, philosopher, unclassifiable sort of person. He built all these true tone instruments. You can do it on trombones and cello, anything that hasn't got frets, you can actually play like that. But he was interested in making instruments which were true tone instruments. So every note you stop on one of those frets is going to be a whole number ratio. So you get to hear music in its pure kind of Pythagorean form. And some people have got really carried away and invented a whole range of fretboards, which you know, I don't quite know what the differences are, but you can imagine people get really into things, don't they? Where were we? Harry Partch. Yeah, there's been a whole history of fudging the scale. I must say, it's not as recent as I was making out. The Pythagoreans themselves noticed that if you put three tones together, it's very close to a fifth, so 9 to 8 3 times. It's almost 3 to 2, but not quite, and then they introduced a thing called a comma, a Pythagorean comma, which is just a little bodge. So they were doing it too. But anyway, on to the next. This is just much briefer. I'm going to talk about the music of the spheres. And this is something which goes back to Pythagoras as well, possibly earlier, but it's attributed to the Pythagoreans. And it's the idea that the cosmos reflects musical harmony. And at that time, the cosmos was understood to be the Earth at the centre, the Moon and the Sun going around the Earth, as they appear to do, and the 5 visible planets, Mercury, Venus, Mars, Jupiter and Saturn, also going around the Earth, and then the fixed shell of fixed stars behind that, so it's a sort of cosmic wallpaper. And they believed basically that we were at the centre of crystalline spheres. Some of you who are doing the Cosmology MA probably know about all this. But the idea was the Earth was at the centre of 7 crystalline spheres, and the planets moved on these spheres. They were perfectly spherical. And on each of these spheres was a siren singing a particular note. And this is obviously like the Greek mythical siren, not like a police siren. And the notes were in harmony. They were making musical harmonies. And Pythagoras and his crew supposedly, or it's been attributed to them, argued that the distances of the shells from the Earth were related to the distances along the monochord. So the ratios of the distances were creating the musical harmonies. So as if like the whole solar system was a monochord, and the planets were spaced out along it to make these different notes, and these sirens were singing on each of the planets and the Sun and the Moon. And this was the musical harmony of the spheres. And this is the basic educational curriculum in the West for 2,000 years, which you don't hear much about now, the quadrivium. These are 4 subjects which were believed to sort of mesh together. So if you went to university, any time from Plato until Kepler, this is what you would have studied. So the 4 things were called arithmetic, geometry, harmony and astronomy. Arithmetic is basically what's called number theory now in mathematics. It's the part of maths which just deals with whole numbers and their relationships and prime numbers, divisibility, simple relationships between numbers, but it's actually a very deep area of mathematics. But number was part of it. Geometry, as in what you'd study at school, the Euclidean constructions and right angles and circles and things. Music, which is mostly harmony, relationships between tones, and astronomy, which then was the heavens, the spheres, as they were understood. And these subjects were supposed to all mesh together, so it made perfect sense in that mindset that the movements of the planets would relate to music, and the music would relate to the numerical ratios, and the geometry of the cosmos would reflect all of this. And this was studied by a whole range of people, as I said, from Plato, Aristotle, Euclid, the father of modern geometry, Cicero, Roman philosopher, Plotinus, of Neoplatonic, Dionysius, is it Areopagite? Areopagite, I don't know how to say that. The Venerable Bede, one of my favourite composers, Hildegard of Bingen, one of Angela's favourite mystics, Ibn Arabi apparently studied the quadrivium, Roger Bacon, who was a sort of pre-science scientist, Thomas Aquinas, Dante, and then Kepler. And it ends with Kepler, here seen in a wonderful rough. Because he's the beginning of modern astronomy. He formulated the laws of how planets move. And he's associated with this, with sort of equations describing how planets move around the sun. It wasn't him that realised that that everything doesn't revolve around the Earth. That was Copernicus, who put the sun at the centre. Kepler latched onto that. He was an early follower of Copernicus, and he deduced these laws of planetary motion. But what's forgotten is that Kepler was basically an astrologer and a mystic, and believed in the harmony of the spheres, in the music of the spheres. That was what he was immersed in. That had been the norm for 2,000 years. And he was living at a time when the data coming in, people observing the stars, instruments were getting better, the data was getting more accurate, and the data wasn't matching what it was supposed to be doing. If the cosmos was beautifully designed to be this musical harmony, hang on, why is that doing that? It's not quite right. So he was trying to work out how to get it to work. So he was devoted to the old cosmology, and in trying to do so, he brought forth the new cosmology. He realised that the planets don't go around the sun in circles, they go around in ellipses, with the sun at one of what are called the foci. The sun has, an ellipse has two focuses, and the sun's at one of them, and the planets go around and they speed up and they slow down, and these two blue areas give you an indication of the relative speed. So this is out here, the planet's going at its slowest. The areas of these areas swept out of the ellipse in equal amounts of time are supposed to be the same. So, and also Kepler related the amount of time it takes the planet to orbit the sun to how far away it is on average, and an exact formula, and it's still taught, it's still relevant. But the reason he was interested in all this is because he thought maybe if you found the ratio between the fastest and the slowest speed of a planet, that would be the note it's playing. And he was trying to reinstate the music of the spheres, and that aspect of what Kepler was doing has been sort of brushed under the carpet because it's embarrassing to modern science that one of the fathers of modern science was thinking about things like that. But something else he discovered which you don't hear much about, and I don't know what to make of this, but I have to be fairly brief with this, but there's these 5 things called Platonic solids. These are three-dimensional objects, there are only 5 of them, and they're characterised by having faces which are all the same, and which all the edges of which are the same. So these are made up of squares, triangles, and pentagons. And if you look at any one of these 5 shapes, it's the same from every perspective, all the edges are the same length, all the faces are identical, and there's no other ones you can construct. And so they were of interest to people going right back to the Neolithic. We have evidence of that. But Kepler had this idea of putting them inside each other, embedding them inside each other, and that sets up invisibly a set of concentric spheres. And it turns out that the radii of those spheres are really close in proportion to where the planets are. There's no reason they should be, no one knows what that means, but this is the kind of thing he was thinking about. And these are his scales. And the idea was, because the planets speed up and slow down, he had this idea, the planets aren't just singing one note, this is what he arrived at, they're singing a range of notes. And these scales, you're going to see, I'm going to show you a few of them, lifted from a book by Jocelyn Godwin, Harmonies of Heaven and Earth. It's a really good source book if you're interested in pre-scientific ideas about music and the heavens. And so prior to this, it had been believed each planet sung one particular note, and Kepler came up with the idea that they sing a range of notes, and Godwin argues that was a reasonable thing for Kepler to have arrived at the time, because polyphony was starting to become the norm, so music involving multiple tones going on simultaneously. So this was the sort of late 17th century version of the music of the spheres. But there were so many versions. Here's Godwin's Harmonies of Heaven and Earth. So I'll just quickly show you. We've got Pliny the Elder, so 1st century AD Roman philosopher. Censorinus, who was a 3rd century Roman grammarian. Theon of Smyrna was a 2nd century philosopher, mathematician. Cicero isn't on this page, but he also had some scales that he worked out for the heavens. He was a 1st century BC Roman philosopher. His scales were based on not the distances of the planets from the Earth, but how fast they were supposedly going. We've got Robert Fludd, who was a 17th century hermeticist, and this refers to Hanshin's manuscript, an anonymous 12th century manuscript. And here we've got not just the planets being given notes in a scale, but the angels as well, and the elements. We've got Berthius, we've got Arabic mystics, we've got another 17th century mystic called Abraham Bartolus. There was a 9th century monk called Eriugena who had his own version of the music of the heavens. There was a 15th century thinker called Giorgio Anselmi. I don't know much about these people. And finally, Kepler, with his Harmonia Mundi, this work he published, the harmony of the world. Oh yeah, Plutarch, Ptolemy, another Arabic mystic. Plato himself had ideas about this stuff. And this is Robert Flood's cosmic monochord, the idea being to illustrate in a single image how you've got the hand of God tuning it, which would be quite useful if you're a musician. The planets and the notes of the scale being linked together. Now, in the last couple of minutes, I'll skip over the Titius braid law. Basically, in the 18th century, someone discovered a strange mathematical rule to work out where the planets lie. And there's no explanation for why it works, but it sort of does, and that added fuel to the fire. And then most recently, someone I know and have worked with on a publishing level, John Martineau, has discovered all sorts of things to do with ratios of planetary orbits, which seem to relate to whole number ratios and musical intervals. And he's published this, it was his master's thesis, in fact, at the Prince of Wales Institute of Architecture and Traditional Design under Keith Critchlow, who's brought the idea of... Keith Critchlow brought Islamic traditional geometry into Western consciousness and is quite open to this kind of thing. So this is a sort of late 20th century version of the music of the spheres. And John has talked about, he hasn't actually done it, creating some computer-based music using the various ratios to generate harmonies and rhythms and make a kind of cosmic music which reflected the solar system. So the idea will not go away. Even though we have modern astronomy, the idea of the harmony of the spheres is still somehow wanting to get out. And I have a theory as to why that is. So the last couple of minutes, I'm going to run past you something that's quite technical, but don't worry about the details. It's more the idea behind it. Basically, it all comes down to one paper published by a French engineer in 2006, which quotes from a book from 1984, and it's a book I'm quite familiar with. My area of interest in mathematics is where number theory, which is to do with prime numbers, basically ties into physics, which it really shouldn't, and this is why I'm interested in it. Number theory is the area of maths that really physicists have no interest in. It doesn't help them in any way, and yet in recent decades it started creeping in. And it's like a kind of neo-Pythagorean tendency that whole number ratios are starting to be relevant in physics again. And GCD here, by the way, stands for Greatest Common Divisor. And if any of you, well, you probably all learned it at school. Two numbers, say 24 and 36. What's the biggest number that goes into both of those? 12. 12 is the greatest common divisor. It's the biggest number that divides into both. Any two numbers I give you, there's always a greatest common divisor. If you can't find one it will do. One divides into everything. So, an interesting and most surprising application of the greatest common divisor occurs in human perception of pitch. The brain, upon being presented with a set of harmonically related frequencies, will perceive the greatest common divisor of these frequencies as the pitch. Thus, the subjective pitch of the two-tone chord, 320 and 560 hertz. Hertz is cycles per second. Now, if you play an A, constant A, it's 440 cycles per second. So that's something a bit lower than an A, it's something a bit higher. 320 cycles per second and 560. So that's the wavelengths and all the frequencies. So you've got these two numbers, 320 and 560. What's the biggest number that goes into both of them? It's 80. So whereas this is called psychoacoustics, people studying how the brain perceives sound. And most people would have guessed that if you played a 320 and a 560, what you would perceive would be the difference between them. But in fact, what you're perceiving is the greatest common divisor. And he argues that if you just shift them both up slightly, so you're listening to 320 and a 560, you're hearing this subjective pitch. I don't quite get what that means, but I think the ear hears a single note when you play two notes. And if you move them both up slightly, it shouldn't really affect what you're hearing because the relationship's still the same, and yet the ear suddenly makes this shift, which strongly indicates that we are perceiving greatest common denominators. And then he gets a bit carried away here. It seems the brain is switching on this kind of greatest common denominator type computer program. Fascinating, unbelievable. Well, yes, it is. But the reason why, and this is what Planat picks up on, Michel Planat, very established French scientist working at the Laboratory of Physics and the Metrology of Oscillators. Metrology is the science of measurement, it's not meteorology or metallurgy. And he's published a lot of papers in peer-reviewed journals. I'm familiar with his work outside of this. This paper was published in a slightly wacky, well, not I shouldn't say that, but a fringy sort of neuroquantology. It's a science journal, but it deals with possible involvement of quantum physics in human cognition or in the nervous system, and that's quite controversial. So a lot of speculative stuff gets published. But he published his paper in 2006, and he quotes from Schroeder. He picks up on this greatest common denominator thing, and he treats that as not just fascinating and unbelievable, but as a clue as to how the brain is working. Because you see, Planart is a metrologist. He's interested in measurement, and measurement is about using instruments. Measurement is sort of the basis of science in a way, because you have to do experiments and you have to gather data, but to get the data you have to measure something, whether you're using a ruler or an oscilloscope or a radio telescope. You're measuring something with an instrument. But then the question is, how do you know your instrument's accurate? You have to measure your instrument. You have to check, and then how do you know that the thing you're measuring your instrument with is accurate? And it gets quite philosophical. And especially if you're trying to sort of synchronise atomic clocks and dealing with billionths of a second, the whole question of what it means to measure something starts to become problematic. Because if things get small enough, you start measuring them, you interfere with them, and then what is it you're measuring? So it's quite a deep branch of science, metrology. And Planart started to branch out and look at biological systems, human systems. How do we work? How do we measure things? So if I give you two weights and ask you which is the heaviest, how are you doing that? If I show you two lights and ask you which is the brightest, or play you two notes, which is the highest, all of these things, you're using your senses to process some kind of input, and you're reducing, and then you're comparing them. And the classical understanding of this is that you're using, as physical instrumentation does, you're using oscillators. You're using something that's pulsing as a kind of reference point to compare things against. Now, the body has electrical systems in it. We've got a nervous system which uses electrical impulses. I don't know enough about the biology of this, but it is understood that at a very delicate level, the body has all sorts of oscillatory systems which could be used as the basis for measuring how hot or cold or heavy or bright or loud or whatever something is. So, okay, fair enough, people want to study how humans measure things, but Planart, applying his quite deep understanding of metrology to that, came across Schroeder's article and thought, whoa, hang on, greatest common denominator, that suggests that we're using quantum physics. Our brain is somehow using quantum theory, because greatest common denominators do not come into classical physics. As I said, number theory just doesn't come into it. When you get to the quantum scale, you're back to a wave mechanics. Okay, so Newton's physics, classical physics, is basically reducing the world to a set of particles that are rattling around, bouncing off things. You're measuring their trajectories. It's like the world is a giant 3D billiard table. That's the classical model. That's generally what was studied until the 20th century. Quantum theory, things start to become more wave-like again. And I can't get into explaining what I mean by that. You've probably heard some strange things about quantum theory. But basically, matter becomes wave-like. Certain physical systems, if they're constrained inside certain spaces, it's a bit like plucking a string or doing this. The reason you get that note is because only a certain shaped wave, only a certain wavelength will fit in whole numbers in the space available. So similarly, if you've got a particle which is also a wave which is oscillating, the frequency has to fit, the wavelength has to fit the space. So suddenly you've got whole number ratios coming out of quantum physics where they weren't there before. So if you see a greatest common denominator thing going on in the brain, it's like, whoa, this is evidence for what people have been suspecting for a while now, which is the brain has evolved to exploit quantum mechanical phenomena for various reasons of cognition. Planart's interested in time perception, not in music, but basically, this is my conclusion, that if he's right, then it could be argued, and in a limited sense, within this sort of reductionist, materialist view, that our appreciation of musical harmony is a sort of side effect or artifact of the way our brains have evolved to use quantum physics to perceive time. So for survival reasons, we need to be able to, just like I need to know how far away something is, if I don't want to trip over it, if I want to kill it or want to run away from it, you need to gauge distances. You similarly need to be able to gauge timescales. This is something we're doing all the time. He's arguing our brain is using quantum mechanical phenomena to do that. It's quite controversial, but Schroeder's greatest common denominator thing suggests he might be onto something. And if that's the case, then when we hear two notes that sound good together, it's because we're hearing these greatest common denominators. So musical harmony is a side effect of that. Now that might seem like a bit, that's a bit disappointing. Is that all it is? You know, because music surely is more to us than that. But my personal feeling that I've come to, or the real conclusion I've come to from all of this, putting this talk together, is the reason that the idea of the music of the spheres is such a persistent idea that wouldn't go away, is because we have this intuitive feeling that music, the musical harmony, is a gift bestowed upon us by the cosmos. And if you were living in ancient Greece, the cosmos is the earth, the moon, the sun, the stars, the planets. So you're going to project that. You're going to think, that must be what is giving it to us. So therefore you imagine sirens singing harmonious notes on the planets, and you try and hang on to that idea, even though it doesn't work anymore once the data is not fitting. But what's really happening is, yes, musical harmony is a gift from the cosmos, but it's not being bestowed from us from above, from the heavens. It's emanating up, it's welling up from the void, or from the vacuum, from the basic structure of space itself, which we're having to use quantum physics to understand at the moment, where whole number ratios start to matter, and where our brains, which are embedded in that space, in order to relate to time, are tuning into these whole number ratios, and we hear harmony, and we like it. And so it's a gift from the cosmos, but it's not from the heavens, it's from the void. So hence the idea of the music of the spheres is a forgivable intuition, which was just a mistaken projection onto the wrong end of the scale, if you like. Anyway, I've overrun by 8 minutes, I'm sorry. But I'll happily answer, or try and answer your questions for the next 22.